Hey, what's going on? It is your boy Jay Bailey here, and I'm back with yet another video. And today we have a pretty interesting challenge. This one is called Lucky Numbers, and it was written in assembler, as you can see. And that's one of the reasons why I chose this challenge, because it was written in assembly, and I wanted to just see what it would look like to reverse engineer one of these type of programs. Spoiler: it's not that different from what we usually do. I guess that should have been obvious, but I just kind of wanted to check it out. This is a level 1, but I actually learned some interesting concepts while completing this challenge, and I'm kind of excited to share them with you all. So without further ado, let's go ahead and get started here. So our binary is lucky numbers. Let's go ahead and just run files so we can see what's going on here. And it is a 32-bit binary, and we see that it's been stripped here. So we can't look at the symbols, but we can still look at the string. So let's go ahead and do that. And we see here we have lucky numbers there, and we see here's that's gonna be the prompt, and it's likely gonna be our success message. And if we fail, they'll say sorry and then get up a super sad face there. So nothing too interesting. So let's just go ahead and dive right into Ghidra. All right, so unlike our previous challenges where I do like a pseudo C like syntax conversion of the disassembly, I'm just going to take some notes here about what's going on in the assembly as we kind of step through it. I won't turn into C-like syntax because it doesn't really make sense to do that because it was written in assembly and not C or C++. So we'll just stick to analyzing the disassembly here today. All right, so let's go ahead and get started here. So we jump to the entry point, and we see that there's a series of move instructions here. And then we also see down here there's this int hex 80 call here. So this is going to be an interrupt here, and it's going to invoke a system call based on what's in this EAX register. And so here we see has EAX is into 4, and so we can sort of decode this system call here if we go to this place here. The link to this site is in the description below, and it's specifically for 32-bit because there are some differences between 32 and 64-bit system call references. But anyways, we see that it was a syswrite here, as you see here, indicated by the EX register gets value of 4. It's a syswrite. And then also tells you what are the other values or other things are in these other registers. So the EBX is going to have the file descriptor, ECX is going to hold the buffer, and EDX will hold how much are you going to write in this case. So let's go ahead and go back to our disassembly. So we know this is going to be a write system call. It's going to be it's going to use the standard output. It's going to write it to standard output, and we'll see obviously this is going to be our buffer here. Then we'll take a look at that in a second. And then here is going to be our how much are we going to write? So we're going to write 15 bytes here. So let's go ahead and jump to this data field here, and we see here this is obviously the prompt here, and if we see the strings there. So let's go ahead and change this though, because it doesn't look very friendly here. Did not want to do that. If you right click on there and hit the string there, it'll turn into a nice little string. So we're going to go ahead and do that for these other ones as well. All right, so now we have some nice looking strings here, and we can jump back to our where the reference is, and we see there it's even cleaned up there. So all this is just pretty much going to print out the lucky numbers prompt to the screen here. And next we see another system call here, and we can analyze what this one's going to be, but you can probably guess what it's going to be. EX gets a value of 3. We'll look at that, and it's going to be a sysread. So it's going to be reading from whatever the file descriptor is. So let's go ahead and take a look at what's going on here. And we see that this is where I learned something new here. And I have to give a shout out to one of my friends in this Discord channel that I'm in. I asked the question, say, why would the file descriptor 2 be used for a read call? That shouldn't be correct, right? Because usually the file descriptors go standard in 0, standard out 1, and then standard error would be 2. So technically this is saying we're going to read from standard error. So that didn't really make sense to me. But what he pointed me to a Stack Overflow answer, which says that whole thing that I just said, 0, 1, 2 being input output error, is actually only a convention. It's not the standard that you have to abide by. So you can indeed say the file descriptor can be standard error, and it'll just read just fine. It'll still take input from our from the terminal here. So that's pretty interesting, and that answer is also in the description below if you want to take a look at that as well. It's not a very long answer, but it's still worth looking at if you're curious. And here we see that it loads up this. Obviously, this is going to be our buffer here that goes into ECX, and it's going to read in 2 bytes here. And so it's going to read in 2 bytes there, and that's pretty much it for this system call here. And now we see that we're actually going to start doing stuff with our buffer here, right? And you see that this is gonna refer to the first character in our buffer, and this will be the second character in our buffer here. So I'll just say this probably isn't very correct, but I'm just gonna say user input sub 0 for that one, and this will be user input sub 1. All right, so we see that we load that into the AL register, right? So we're gonna say AL is equal to user input sub 0, and then we subtract hex 30 from that, minus equals 0 hex 30. And so we've seen stuff like this before, right? So we know when they perform this action here that they're usually trying to get the actual decimal value of a number, right? So like if we were to type in the number 8 into the terminal or as input, it's gonna interpret that as hex 38. And I guess the author wants the actual decimal value of that, so he subtracts hex 30 from this value. And then we see we do the same thing for BL, right? So we said BL is equal to user input sub 1 this time, and then BL minus equals 0 hex 30. So now we have 2 decimal numbers here. Oops, didn't mean to do that. Cancel. So now we have 2 decimal numbers. So assuming I put 77, we now have 7 and 7, like hex 7 and hex 7 in there, not hex 37. And then we see there's this add with carry here. And I don't think we've ever seen this instruction before. So what this does is, it, as the name implies, it adds these 2 registers together, stores it in the AR register, but it also will add the carry as well. So assuming that one of these values resulted in in the carry flag being set, it will add that value back into, it will add 1 to the result here. So that doesn't make sense. It looks something like this. So ADC would be operand 1 plus the carry flag plus operand 2, and that's how it's going to look here. So it'll be in this example AL plus the carry flag plus operand 2, or I guess BL, right? And that's pretty much it. So the carry flag could be set in either one of these instructions here, and that would likely change the value of our addition here. And then we get to this instruction here. Now this instruction confused me for the longest time. I was lost. I had no idea what it did. It didn't make sense as to why it was doing it. And I found a wonderful tutorial about what this instruction does and how it works. That's in the description below. I'm gonna try and go over what the guy said, but if what I say does not make sense, watch his video. He will do it way more eloquently than I can do. The video quality is kind of low, so like the first 4 minutes, the video quality is not that great, but he's getting some really good examples. And then from about the 4 minute mark, 4 minutes and 20-second mark, the video quality improves, and he really goes through a lot of the different examples. And so I'll try to do the same thing here. But so just bear with me. I'm still kind of wrapping my head around it, but I think I understand it well enough to explain it now. So let's go ahead and get started. So the DAA instruction, it stands for decimal adjust AL after addition. So it's going to adjust the AL register after an addition here. So we just performed an addition, obviously. So this instruction is going to adjust it after this addition here. But how is it? What does it do? Why does it do that? And how is it going to do it? So the purpose of this instruction is to try to convert hexadecimal numbers back into their decimal format. So when we type in a number here, right? So if I were to type in, let's say 88, the computer is going to recognize that as, I think it's hex 58 here, right? So like when it gets the value, it's going to say hex 58. So if I were to say I want to add 88 plus 88, it'll be hex 58 plus 0 hex 58. And then the answer that it gets is going to be, this is going to be B0, 0 hex B0, right? And the reason is that because, well, I mean, I'm not trying to insult you. If you already know how to do hex addition, you can kind of skip over this a little bit here. But like, you know, it's somewhat important. So you have hex 58, and then you're gonna add 8 plus 8, which is gonna be hex 10, because that's 16. So the carry flag will be set here, and then this will be 0 hex. So 5 plus 5 is A, which is 10, plus 1 is B, so that's gonna be B, 0. That's how we get the answer. But we don't really know, we don't deal with that in the real life. Like when I type in 88 plus 88, I want 176. That's what I expect to get back, because that's I don't deal in hexadecimal numbers all the time, and honestly I wouldn't be able to just eyeball this and be like, oh, that's 176. I wouldn't be able to do that. So so the DAA instruction is used to convert the hexadecimal number back to decimal, and so and we'll kind of go through a few examples. So let's just say, so how it will convert this one to a decimal here. Actually, let me back up here. So this number here, hex 58, is comprised of two nibbles, a lower nibble and a high nibble here. So the higher nibble is going to be 0 hex 5, and the lower nibble is going to be 0 hex 8. And actually, you can probably think about 0 hex 05. Well, maybe not. All right, so this is the higher nibble here. Oops, this is the higher nibble. That's the lower nibble. So when we get a result, we have to do something here. So to convert this back here, but there's a few routes we have to check. So if the lower nibble is greater than 9, then we add 6 to the lower nibble. The other condition is if the auxiliary carry flag is set, then you also add 6. Now, if you don't know what this auxiliary carry flag is, you're not alone. I had no idea what that crap was, but like I said, the guy in the YouTube video, he really laid down the law and explained it very well. So this is actually an example of it right here. So if we were to take this number here, when we add 8 plus 8, we get 1. We carry the 1 here, and we add 0 down there, because 8 plus 8 is 16, but there's no 16 in hexadecimal numbers, so you carry the 1 and you bring the 0 down. This 1 up here is the auxiliary carry there, so the auxiliary carry flag would be set in this case. So we have to add 1 to the lower nibble there, right? And so we would say, we add 6 to the lower nibble, so we would have 0 hex B0 plus 6, which give us 0 hex B6. But we still have this B in there, and we don't need that either. Well, so now we have to look at this. So the other rule is, if the higher nibble is greater than 9, or the carry flag is set, I'll just say CF, then you add 6 to the higher nibble. Right, and so in this case, the B is obviously greater than 9, because B is what, 12, I believe, 11. B is 11, and so we're going to say, all right, so 11 plus 6 is 17, right? So the answer will be 176, and we now converted this B0 to this this value here. And so that's kind of the purpose of this instruction here. It's going to adjust the AR register back to a decimal formatted number, right? So I hope that makes sense. I have some examples on my blog here. So if you go to my blog, you will see that I have a few examples that kind of go over the same thing that I just talked about. And then again, and so like you can take a look at that. Or you can also take a look at the YouTube video, or you can ask me a question in the comment section below if what I said did not make sense. All right, so now that we know that after this instruction executes, the AO register is essentially going to be some type of decimal number, right? So we know that for a fact now. So now let's see what happens next. So I'm going to do that. I'll just say DAA. And then we see that the BL instruction, or the BL register, gets added to hex 30 now. So BL plus equals 0 hex 30. And so now BL is essentially a ASCII encoded character again, right? Because all we did was subtract hex 30 and then we added hex 30 back to it. So we'll keep that in mind. So then we see that we're going to compare AL to the hex 16 here, right? So if AL is equal to 0 hex 16, well, if it's not equal to that, we see we jump up here, and then we see we get this error message there. So we obviously don't want to be, we obviously want it to be equal to hex 16, and then BL as well is compared to hex 38. So BL equals to 0 hex 38, and if it's not equal to hex 38, then we see that it's going to again give us the error message here. So this is essentially like an ANDed if statement here. At least that's how I'm interpreting it there. And I'll add some extra parentheses there. May not be necessary, but I'd like to be sure. So if both of these are true, then we print out the good job here. All right. And so now we have to figure out, so what do we have to type in order to get these values here, right? So we know that we have when we type in any characters, any two numbers here, it's going to store in the AL and BR registers. And we know for a fact that the BR register has to have the number 8 in there. And we know it has to have 8 in there because it gets compared to the ASCII version of 8. And BL doesn't really change at all, really. I mean, it gets changed here, but it gets changed right back, or right back here. So BL is essentially going to be the same value when it comes in and when we come out of this comparison here. So BL has to be 8. What about AL register here? We see it gets compared to hex 16, but we have to also remember that this DAA instruction is going to modify what's in this register here. So let's go ahead and do a little bit of algebra here. You may already know the answer, but if you don't, let's just bear with me here. So we know that AL plus BL has to equal to 16 here, hex 16, and we know that because we add these two together, it also gets compared to hex 16 there. But since this DA instruction is going to change it back to a decimal number, we can kind of look at this as, instead of hex 16, just 16, because that's essentially what it is at this point. It's comparing it to, yes, a hexadecimal number, but it's actually comparing it to a decimal value that we got from here. All right, so let's see. So if we solve for AL, right, just like in algebra class, you remember this, 16 minus BL. We know that BL has to be equal to 8, so 16 minus 8. And then that means AL has to be equal to 8, obviously, right? And so let's go ahead and I'm going to prove this to you really quickly. So if I were to add 0 hex 8 plus 0 hex 8 here. So if we add these two together, it's going to give us the value of, actually let me write this like this here. So we're going to do the same thing, and actually I'm going to say 0 8 here to make it a little bit easier to follow. So if we had 8 plus 8, it's going to give us what? It's going to give us hex 10, right? So the 1 is going to be the auxiliary carry here, and then we're going to have a 0 right there. And then this 1 here, kind of just 1 plus 0 is just 1. So that's the answer there. But if you remember, if the auxiliary carry flag is set, we have to add 6 to the lower nibble here. And this here is going to be our lower nibble. So 0 hex 10 plus 0 hex 06 will give us 0 hex 16. And that's our answer. And that's what we want it to be. So if we were going to prove this out here, if we lucky numbers 88, there it is. So not too difficult, but also it can be a little confusing because of that whole DAA instruction. It definitely threw me for a loop. But I hope you learned something. Hope you enjoyed this video. If you did, give me a like. I really appreciate that. If you have any questions, if something just wasn't very clear or didn't explain something very well, please leave your question in the comment section below, or you can hit me up on Twitter, Instagram, Discord. I'm pretty available. If you have like a challenge you'd like me to try and solve, leave that in the comment section below as well. I can't guarantee I'll solve it right away, but I will do my best to try to solve it at some point. And if you enjoyed this video and you want to see more of this type of content, then don't forget to subscribe, hit that bell icon so you're notified when the videos go live. I'll see you guys in the next one. Peace out.